Hello and welcome again to my Physical Science Online video lecture and lab supplement series. Today's video is another of our post-quiz reviews. This time we're going to be reviewing the quiz from the Lens Lab. So let's go ahead and get the quiz pulled up. So let's open it up and see what's inside. Our first question is a pre-lab warm-up question, and it asks, what did you use to focus the light in this experiment? So given that this lab is called the Lens Lab, and given that it says that you're going to need a positive converging lens, that is, for example, a magnifying glass, then it follows that the thing that you're using to focus the light must be a lens. Next, second pre-lab question. Suppose your lens has a focal length of 20 centimeters. At which of the following distances could you place the candle if you followed the instructions of this lab? Choose all which apply. So we open up the lab instructions again, and you actually have to kind of scroll down a little ways before you get to the part where it's talking about that. It has to do with the third method for measuring focal length. And basically what it says is use only object distances which satisfy DO greater than F. The object distance is DO, F is the focal length. So if focal length F is 10 centimeters, then you always have to place the candle farther away from from the lens than 10 centimeters. So that means that the answer to this question, we're given focal length 20 centimeters. We need to use distances which are bigger than 20 centimeters. These three distances are all bigger. 50 centimeters, 25 centimeters, 1 meter. 1 meter is 100 centimeters. Okay, the next thing that it asks is that it says you should basically focus the sunlight onto a piece of paper, and you find the spot size as being 1 centimeter. And then this is when the paper is 20 centimeters from the lens, and then again the paper is placed 30 centimeters from the lens, and it asks what's the focal length. So the spot size is 1 centimeter in diameter at these two locations. So if you open up the handout again, it basically will tell you, we got to kind of scroll back up, this is actually the second method. It tells you that sunlight can be focused into a small circle, and so for example you can do this to a radius of 1 centimeter, 1 millimeter, etc. In this case we did a half a centimeter radius because the diameter is a centimeter. And basically any time that this happens where you're you're focusing the sunlight into a circle that is larger by a significant amount than the focal spot size and smaller than the actual size of the lens by a significant amount, that there will be two locations at which this happens, and that the average of the two distances should also equal the lens's focal length. So if we come back in here, it basically just said that the two distances are 20 centimeters and 30 centimeters. So basically what we use is that the focal length is equal to the average, so 1/2 of 20 centimeters plus 30 centimeters. And so this is 1/2 of 50 centimeters, which is 25 centimeters. So the focal length in this case is just 25 centimeters. So we enter 25 here. Question number 4 says, you focus the sunlight onto a piece of paper and find that the light seems to be most nearly focused between 24.8 and 25.2 centimeters. So what is the best guess for the focal length of the lens? So we can open up those instructions again. This is actually referring to the first method. So we're kind of going in reverse order of methods. And it basically says use the sun and hold the lens so that it focuses the light onto a viewing screen, for example, a blank index card or a piece of paper or so on. And basically, you want to find the distance at which you can hold the card, which gives the smallest point of focus for sunlight. The distance between the lens and this point is the focal length. So it then says basically that there's some range over which sunlight may be appeared to focus to a point. And in this case, the focal point is in the middle of the range. And the range's size gives an estimate for the uncertainty of the lens focal length. Okay, so here, for example, it says that the range is between 24.8 and 25.2. So we want to know what's in the middle of that range. Well, the middle of that range is 25.0. So we can enter 25 here again. Then it says you focus sunlight on a piece of paper and find that the light seems to be most nearly focused between 24 and 25 centimeters from the lens. What is the uncertainty in the focal length of the lens? Okay, well, basically, since you have 24 and 25 as the extent of the range, we can go back to those instructions, and it's basically the range's size gives an estimate for the uncertainty of focal length. For example, if the sunlight is focused to a point over a distance 15 to 17 centimeters, then the focal length of the lens is probably 16 centimeters with an uncertainty of 1 centimeter. 1 centimeter is half the difference between these two. So 17 minus 15 gives you 2. Divide that by 2 and you get 1. Well, in the problem that we're actually being asked here, you have 24 and 25. So 24 minus 25 is 1, and if you divide that by 2, you get 0.5. So the uncertainty is 0.5 centimeters. Question 6 asks, suppose you have a lens whose power is given as 2.5 diopters. The D is for diopter. What is the focal length of this lens in meters? So let's pull up those instructions again. And basically what that's all about is that lenses often give focal lengths in diopters. And so down here, they give a power in diopter, excuse me. And basically you can compare your three methods to each other, and if your lens is a known focal length, calculate the percent error for each method. So the way you get the known focal length for the lens is that a lot of lenses will tell you that they have a power of, for example, 2 diopters or 3 or 6 or 10 or whatever. And the relationship between power and focal length is that the power is in diopters is the inverse of the focal length in meters. So if you have a power of 2 diopters, and the focal length is a half a meter. And if it's 4 diopters, then it should have a focal length of a quarter of a meter. So coming back up here, we have that the power is given as 2.5 diopters. So opening up our little workspace, power is equal to 1 over focal length. So that means that power times focal length is 1. And so that means that the focal length is 1 over the power. So in this case, we have that the focal length is 1 over 2.5 diopters. And a diopter is the same as an inverse meter. So if you need to, you can divide 1 by 2.5. You should get about 0.4. So you have a focal length in this case of 0.4 meters. So the question itself is asking us to find the focal length in meters. So we should put the answer in meters, 0.4. Okay, next question. The image is measured as being formed 12.5 centimeters behind a lens. What is the reciprocal of the image position? 1 over di in inverse centimeters. Okay. Well, there's two parts to this. One is what is the magnitude, and the other is what is the direction. The direction is specified by a plus or a minus. And the general rule is with a lens, if the image is formed in front of the lens, then it's going to be a virtual image and it's going to have a negative distance. If it is formed behind, or a negative position maybe I should say, if it's formed behind the lens, it's a real image and it's going to have a positive image position. So the other part of it is finding the magnitude. So we've been given that the distance to the image di is 12.5 centimeters behind the lens, so basically plus 12.5. That means that the inverse of this distance, 1 over di, is 1 over 12.5 centimeters. And so what that gives us is, if we open up our calculator, I think it's going to give us 0.08. So 1 divided by 12.5, 0.08. So the answer then is that 1 over di is 0.08 per centimeter, or inverse centimeters. So we can open up this guy here and we put in 0.08. Question number 8. Which of the following can you best use to obtain the focal length of the lens, assuming that you have made a plot of the reciprocals of the image and object positions? That one may be a little on the tough side to answer just offhand, but if you look in your directions, it basically says, here's your third method. You take 8 to 12 data points and then you make a good graph of image distance versus object distance. And then basically what you end up doing is you graph the inverse of image distance versus the inverse of object distance. And when you do that, you end up getting a graph that looks basically like this. It's basically a straight line. Now, what happens where this line hits the intercepts? Well, at the x-intercept, that implies that you have 0 here for 1 over the image. At the y-intercept, you have 0 for 1 over the object position. And if you go up to these equation up here that's given, 1 over do plus 1 over di is equal to 1 over f. So if you put in a 0 for either 1 over do or 1 over di, then what you end up with is whichever of these is left over equals 1 over f. So that basically means that both of the intercepts are going to give you the focal length. And so that's getting into these questions down here about analyzing and interpreting your graph. So let's open up the quiz here. Basically, we find that the x-intercept and the y-intercept give you the reciprocals of the focal length. And so if you take the reciprocal of either one of those, you get the actual focal length. Here, by the way, I have actually put that same graph that I just showed. And it basically says the reciprocals of the image distance and the object distance are plotted against each other. And it asks, what units will the slope of this line have? You didn't do much with the slope of the line in your lab other than hopefully find it and find the units of it and realize that it's not what you were looking for. But if you did in fact do that, you will notice that the slope of this line has to be a change in this divided by a change in this. And this both have the same units. They are both meters to the minus 1. So that basically means that if you took the slope, you'd have meters to the minus 1 over meters to the minus 1, and so that leaves you no units. So looking through these options, none of the above is the correct option because unitless isn't listed here. This one now, number 10, is asking what are the units of the y-intercept? Well, the y-intercept is basically going to be up here somewhere. It's some number that's on this line. This line is in inverse meters, so we choose inverse meters. And again, you can see that if you come down to the graph that I've made. Actually, you can maybe see it a little bit better here. You can see that there is in fact a minus 1 in this units here. So if I put a little space in, you can see the minus 1. Okay, so that gives you the units that go with that particular graph, both for the y-intercept and for the x-intercept. So now it says refer to this graph. What is the focal length of this lens in meters? So looking at this graph, it appears to me that this line seems to have an x-intercept of 3 and maybe a third or 3 1/4, somewhere in there. This is 3, this is 4, this must be 3.5. This looks like it's a little closer to here than it is to here. So let's call it an intercept of 3.3. So 1 over f is equal to x-intercept, which is equal to 3.3 inverse meters. Therefore, f must be 1 divided by 3.3 inverse meters. So basically 3.3, we take the inverse of that and you get something like this. And so the focal length must be approximately 0.303 meters. And the question asks for us to basically answer in meters, so it's sufficient at this point to just put 0.303 or whatever. In fact, the tolerance on this particular question is fairly large, I think. I think you can have like 0.30 if you wanted, and it should count it correct. Okay, what happens to the image if you place the candle closer to the lens than its focal length so that DO is less than F? So this is because you're asked in the question down here, what happens if you decide to place the candle closer to the lens than the focal point? So you should have actually done this in doing the lab, and so you should just be writing down what it is that you observed. So one way that we can actually attempt to do this is to have the simulation of this thing, because that's going to be the easiest thing to show you on the screen. So this is from the University of Colorado's physics education team puts these simulations together. And if you watched the video in preparation for this, then you've actually seen this simulation already once. What I'm going to do is I'm going to tell it to show the virtual image if a virtual image is formed. So right now this is the object. If I move the object, it moves the image. I can't actually move this thing. I can only move this because this is the object. And this little X is actually the focal point for the lens. So I need to move this closer than the focal point. Notice as I get closer and closer to it, the image is getting formed farther and farther away. And then all of a sudden, when I move past the X, you see these green lines appear. And so here's the image. And if I turn off virtual image, it goes away. So this means that it's forming a virtual image. And then looking at the orientation of everything here, it looks to me like this is larger than the object. Looks like it is upright, whereas when I had the object back here, the image is actually upside down or inverted. So here the image is upright, and no matter how close I get to the lens, it's always farther away from the lens than the object. So it should be upright, bigger, virtual image, farther away from the lens. So let's see which of those options are actually available in this quiz. Image is upright or image is inverted? Well, it's got to be upright. Image is real or image is virtual? Well, the image is virtual here. Image is larger or smaller? Well, it's larger. Okay, so we shall submit. Accepts this thing. Let's review our results. 125 out of 100 points. Here's your 25 extra credit. Everything else is correct on here, so you have now all the answers to this quiz. So that brings me to the end of today's video. I hope that you found this helpful, and thanks for watching.